Welcome everyone to the session 24 of our STEM talks here for the 7th Polygence Symposium of Rising Scholars. My name is Ali and I will be moderating today's session. The goal of the symposium is to celebrate and showcase the hard work of our Polygence scholars, all of whom have tirelessly worked on their projects over the past couple of months. We do have 2 students presenting on a variety of topics today. A fellow member of the Polygence team will be scoring each student's presentation, which will help us determine prize winners after the event. So please just type your questions in the Q&A if you have any questions for each speaker, and we will have time at the end of the session for the speakers to address those. We'll give it, I think, another minute or two for some audience members to join us, and then we can go ahead and start it off. Hi, Krey.
Hello, how are you?
Hi, great, thanks. We're just going to give it a few more seconds here, and then we can go ahead and get started.
Is there a specific order that we're going in?
Yes, so I think we're going to have Ari's going to go first. Okay. Krey, you'll be second. Sure. And then Nikhil, you'll be last. And I can call you guys into that when we get started. Yeah.
Okay, thank you.
And then I just asked Krey that when the person who's speaking is on, just keep your audio muted and your camera off. So.
Of course.
Okay. Okay. Okay, now that we're all here, let me just make sure that I can. Perfect. Okay. I think we're good to go here. So let me just go ahead and restart here. So welcome everyone to the Talk 24 session for our STEM talks here today at the 7th Polygence Symposium of Rising Scholars. My name is Ali and I will be moderating today's session. The goal of the symposium here is to celebrate all of the hard work of our Polygence scholars and to showcase this hard work to all of you. They've worked tirelessly on their projects over the past couple of months. We have 3 students presenting on a variety of topics today, and we do have a fellow member of the Polygence team here that will be scoring each student's presentation. This will help us to determine the prize winners after the event. So if you have any questions for our speakers, please feel free to type them into the Q&A portion of our chat here, and we will address those at the end of the students' talk. So today's speakers, we have 3, the first of which we have Cheng, then Krey Daniel and Nikhil Devireddy, who will be talking to us and sharing all of their great research that they've done in the STEM world. So let's go ahead and start off. Ari, if you would like to kind of share your screen with us.
Okay. Can you see that? Or...
Yep, looks great.
Okay. So hi, my name is Ari, and today I'll be presenting my project, which is on computationally modeling exoplanet spectra. So first, I'd like to introduce this field. So exoplanets is short for extrasolar planets, which just means planets that orbit stars other than our sun. And this is a relatively new field of study. So the first exoplanet was actually discovered a little more than 30 years ago in 1992. And I believe that this field is really significant, even though it's not something that we encounter on a day-to-day basis. I think this is our best chance at looking for extraterrestrial life, which is something that our species as a whole has been thinking about for thousands of years. Is there life out there? So I think this is our best chance of looking for this kind of thing. It also provides future directions for exploration, so we can characterize exoplanets. We can know if they're suitable for life. And notably, there's this planetary system around a star called HR 8799, where we've discovered evidence for water and carbon monoxide in 3 of 4 planets. And these are 2 very strong potential biosignatures. So the way we do this is through a method called direct imaging. This is a fairly recent advancement. I think the first discovery made using this method was in 2008. So if we look on the picture to the right here, you can see 3 blue specks on the right side of the image, and those are actually the planets that we can see. And that black circle in the center is the star where we've blocked out all of its light, so we can actually see the much dimmer planets. And through this method, we can observe the spectrum of light passing through the exoplanet's atmosphere. And then from this, we can determine the existence of certain compounds, because the compounds will absorb light at certain wavelengths, and those wavelengths are specific to each molecule. And that kind of information is available in these absorption line databases. However, the spectrum that we receive will almost never resemble the raw data from these databases, because as I will present shortly after, there are a ton of different effects that can kind of modulate the spectrum. And the really high fidelity accurate models will have to take all of these effects into account, and then they will be used to interpret the kind of real observations that we can get. So the method I'm presenting here is similar to a library developed in 1994, and this library is still in use by NASA and other institutions worldwide. The database that I will be using is called HyTran. It was first developed in 2008, and it is updated regularly. And my model here is only a first order approximation, so I'm only going to consider the most prominent and widespread effects, which include radial velocity, line broadening, Zeeman splitting, and the background blackbody radiation. So here I'm just going to give a brief overview of each of the effects that I talked about. So the first is blackbody radiation, which is just continuous electromagnetic radiation emitted by any object above a temperature of absolute 0. The second is radial velocity. So this actually describes the planet's motion relative to our instruments, and that will induce a Doppler shift on the spectrum. So from that Doppler shift, we can determine how quickly the planet is moving relative to us. And then Doppler broadening. So this is kind of similar to radial velocity, but applied to individual gas molecules. So because gas molecules will be in random thermal motion, because they're at a temperature above absolute 0, they will have individual Doppler shifts. And we actually measure this as a broadened absorption line. The second broadening effect is called pressure broadening, where collisions between gas molecules will perturb their energy levels. And because the absorption line of a molecule depends on the transition between energy levels, this will cause a change in that. And it is also observed as a broadened spectral line. The third and last broadening effect that I'm going to talk about here is called rotational broadening. So this is where a planet's rotation causes relative motion to the observer. So essentially half of the atmosphere will be moving towards the observer, while half of it will be moving away. So this is basically another instance of Doppler shifts, and this is also, as I said, measured as a broadened spectral line. And the final effect here is called Zeeman splitting. So this is where a magnetic field can actually change the energy levels of an atom or a molecule. So most of the times this comes from changing the energy levels of the electrons, but if we have a charged particle, this can also just impact the particle as a whole instead of just the electrons. And the reason I chose these effects are because they are the most prominent in that they have the most noticeable effects on the spectrum, and they also occur in almost all observations of all exoplanets. There are some niche kind of effects, called limb darkening, but that is kind of only prominent in planets that have a lot of light originating from them because they're relatively young and self-luminous, and not applicable to all planets. So the reason I chose these 6 is because they will occur in almost all exoplanets that we look at. So here's a sample output from my model. So a spectrum basically graphs the relative intensity or flux of the light that we can receive as a function of wavelength. So each of the different dips here that you can see in the graph represent an absorption line. So that basically means that at that wavelength, light will be absorbed by certain molecules in the atmosphere. And the molecule that I'm modeling here is actually carbon monoxide. So this is called the first overtone band that appears at around 2,300 nanometers. And it is a very distinctive feature. So basically, if we see this kind of spectral feature from an exoplanet spectrum, we know that that exoplanet probably has carbon monoxide in its atmosphere. And from this, we can also determine some other properties which impact the spectrum that, like I described earlier. So in addition to just the molecule, we can also use it to interpret real observations. So researchers in this field use what's called a cross-correlation function, or CCF, and that kind of gauges the similarity between 2 data sets. So in practice, we're going to take a model spectrum, like the one that I showed in the last slide, and we're going to compare it to a real observation. And what researchers do is they generate millions and millions of model spectra and then see which one matches the closest with the observed one. And the one that matches the closest is likely to be the one that best describes the planet's properties, like its temperature, its pressure, all the things that can cause an effect on the spectrum. Now, in practice, this is very inefficient and slow because it is essentially a glorified version of guess and check. So researchers will use what's called a grid of model spectra. So that's basically just a library of pre-generated spectra, so they don't have to generate a new one every single time. And they also use a couple of other techniques to kind of cut down on the computation time. So they're only going to consider the regions with a higher correlation. But even with all of these kind of shortcuts that we can take, these processes can still take up to days and even weeks to complete. So this is by no means a quick process. So finally, I'm just going to talk about the limitations of our techniques and kind of future directions. So cross-correlation is not a perfect method. It's basically guess and check, but if we consider like 2 kind of parameters that can have a similar effect, then this method won't be able to distinguish between those. So if we have rotational broadening and pressure broadening that can both make an absorption line broader, cross-correlation is not going to be able to tell you which one it is. And this is where we have to use human intuition. So we can set an upper bound and a lower bound for reasonable values of a certain parameter. So we can say that because we're looking at exoplanets, we're going to bound the temperature to 1000 Kelvin or something like that. But again, this is not something that we can automate, and it is where we need human intuition. And finally, the models that we have as a field just can't simulate a 3D atmosphere. So most of the models that are in use in the field are 1D models, in that they simulate the atmosphere kind of as a line or a gradient of certain values. And there are recently developed 2D models that basically model an atmosphere as like a plane. But the model that I'm presenting here is 0-dimensional, in that I'm only taking 1 point or 1 value for all the different parameters. So the entire atmosphere is collapsed into a single point, and this is obviously not going to be accurate, but for the purposes of exoplanet spectroscopy, it is actually good enough in that the uncertainty or the error with these kind of simplified models is less than the experimental or observational uncertainty that we can get from our instruments. So thank you. That was all that I had. And are there any questions?
That was great, Ari. Thank you so much. Wow, that's like incredible that you were able to kind of do that and explain it so well as well. So we have a few questions from the audience here. The first of which is someone asked, what was the impetus for you to pick this topic? I guess what drew you to this research?
So again, I think this, what's special about this field is, I guess, the potential to find kind of extraterrestrial life. This is something that I've, been interested as a kid, are there aliens out there that we can find? And this is kind of a way that we can kind of get to that sci-fi future without like being too non-scientific.
Mm-hmm. Do you think that there are aliens, extraterrestrials out there?
I think that there definitely are. We just haven't found them yet.
Mm-hmm. Yeah. Very cool. I was talking to a friend of mine actually about that just the other day. We were having that debate. So we have, another question from the audience here, which was, how much does human intuition reduce the parameter space?
Sorry, could you repeat that?
How much does human intuition reduce the parameter space?
So it's actually not a lot, because when we're considering an exoplanet, we don't have any prior information because it's just so far away. So the most of the information we can get is from the spectrum, and then we're trying to back out that information. So what we can really say is it's a planet, so its temperature won't be that high, but we just don't have a really strict bound. So most of the times we can bound this between 1000 Kelvin, but that's pretty much as accurate as we can get.
Okay. And then sort of, relatedly, we have another question here. What was the most challenging aspect of this project?
So the most challenging one was definitely writing up my model, because I don't have that much experience in coding. So it's basically learning as I went. So this entire, a big part of this project was being able to actually generate these model spectra. And then that was really challenging for me to kind of just learn a coding language.
Absolutely, yeah. As someone who's also trying to learn code, I can totally relate to that notion. Well, this was really excellent. Thank you so much, Ari. I think we can go ahead and move on to our next speaker, which I believe will be Krey. So let me grab my. Okay. Great. So Ari, if you want to go ahead and stop sharing your screen, and then Krey, you can start sharing.
Of course. Just give me 1 sec. Is my mic okay?
Yeah, of course. Yes, sounds great. Yep.
Sure. Okay, you can see this?
Great. Yep.
Okay, there we go.
Great.
So, hello, thank you for coming and listening to my talk today. Today I'll be going over this quick review paper I wrote about the NF-kappa B pathway, which is a cellular signaling pathway, and its use in cancer pathogenesis, basically how we can use the signaling pathway to address cancer and how we can use it to fight cancer. And I'll get into what all this means in the presentation. So just to start with some background, the field that this is basically looking into is cancer development, like cancer, and its ties to inflammatory signaling pathways. So basically, inflammation is a bodily process that is used for a couple of different things, but mainly for fighting pathogens and repairing tissues and things like that. And this is a natural body process, but it has a lot of ties to cancer development, and it can be both positive and negative when in a cancerous situation. Because on one end, inflammation that your body initiates, it can help to fight cancer. But on the other end, if it's misregulated, if it becomes part of that cancerous, if the tumor is able to utilize that, it can actually be the very pathway that pushes the cancer forward and pushes it to develop further. So there's a lot of research being done into the ties between inflammatory signaling pathways and its ties to cancer development. So in recent years, there's been a lot of research into that. So what I'm specifically talking about today is one specific pathway, because there are so many different inflammatory pathways. There are like millions of different signaling pathways in our cells, in our tissues, and there are so many different inflammatory pathways. It takes way too long to address and research and talk about each and every one. So what I'll be talking about today is called the NF-kappa B pathway, and it is a pretty large, pretty important inflammation pathway. And basically, in recent years, in the past, what has been done with this pathway, the most research that has been done has been focusing on this one specific molecule called COX-2 or cyclooxygenase 2. And basically, it's an enzyme that catalyzes a set of proteins. I'm not going to get too deep into it, but basically it starts off a whole chain of different signals that sets off a huge inflammatory pathway. And that in a cancer situation can lead to a lot of problems, a lot of like worse cancer development. So in the past, this has been one of the main targets for researchers to try to regulate this specific molecule, and in the aim of course, like reducing cancer growth. But the thing is with that is that the current treatments that have resulted from that, specifically because they targeted this one molecule, there's been a lot of adverse side effects. And there have been like all the different treatments they come up with, which are basically, they call it COXIBs and NSAIDs. Basically, they go out and they regulate the molecule, and they would suppress the amount of that molecule that's made. But because of the importance that it has in the pathway, it causes a lot of like side effects. So basically the premise of my project is kind of going off of that basically, since these current treatments have been like mainly focusing on this one molecule or just a couple different options, I think it'd be very helpful to explore as many like alternative options, or different molecules we can target, different signaling pathways that we can figure out how to regulate with the aim of fighting cancer, but avoiding as many like side effects and disadvantages as possible. So what I did in this paper was basically go through a couple different types of treatments we can do, and I chose a few different molecules and different things that we could target potentially, and I evaluated all these alternatives. So just a quick overview of what we'll be going through. Basically, I'll start with what are called small molecule treatments, which are small molecules are just these very small molecules that can easily pass into the cell and go target a whatever molecule you make it go target. And they're very easy to use. It's a field that's been around for pretty long now. So there is a lot of testing that has been done with it already, but there's so many different targets that we haven't explored yet and things like that. So that's a good topic to explore. Then I'll be going into nucleic acid therapies, which are basically using like RNA and DNA strands to go and target whatever molecule we want to target in the pathway. Then that's a little bit of a newer field. And then finally, I'll be talking about antibody-based therapies, which is a very new field. It's basically using antibodies to go find a cancer cell, find the specific receptor molecules on a cancer cell, and then go target those cancer cells. So that's a very new field. So there's not much research that's been done yet. And then finally, I will finish up with a couple like evaluations about each treatment that I found. So starting with small molecule treatments, there's 4 different things that I want to talk about, starting with this molecule called CRO. So the pathway that I mainly focused on in this project. It's called the NF-kappa B signaling pathway, and it's just one pathway out of so many different pathways in our cells and tissues. And this this pathway contains a specific molecule called NF-kappa B, and it's a protein complex, and it's essential to the pathway. So like it's a chain of different molecules. This is one molecule in that chain. And CREL is basically a subunit of that molecule, subunit of that protein. And there's been research done recently where when they did CREL ablation, basically deleted that subunit of the protein, it led to a decrease in Tregs, which is basically, Tregs are regulatory T cells, and they're some of the main cells that carry out your inflammatory processes. And since these Tregs were reduced, that those inflammatory processes were also reduced, and that actually helped cancer suppression, and it led to a lot of actual results in cancer decreasing. So that's we haven't properly explored that, but there was like one paper that was done recently. So it has a lot of potential, that specific molecule. Then I wanted to talk about these TLR and TNFR receptors. So these are both receptors. Receptor molecules are basically these proteins that will be on the outside of your cell, on the surface of a cell. And they will detect different signals that come from external, like from outside the cell, and they will react to those signals and start a pathway inside the cell, start a different chain signaling pathway inside the cell. So basically, they're basically like the very start of the pathway in the cell. So they'd be a really good target to regulate. And there's been some research into like a very specific receptors, the TLR4, TLR7, 8, 9. And there were some side effects that came from that. So there's been some caution, but it's a huge family of different types of receptors. It's called a TNFR superfamily, as you can see. And there are just so many different targets that are possible. And there's a lot of area for research and looking into what we can do. Then we have proteasomes. So proteasomes are basically proteins in your cell that break down other proteins. And basically it's to regulate the number of like proteins and molecules you have in the cell. If there's too much, if there's too much of a certain protein, those proteins will be tagged and they'll go to this proteasome and they'll be broken down. So it's to like regulate. So obviously that's a really essential function in the cell. So again, anything that's like really essential in a pathway is a good target to regulate that pathway. So there's been some research into that. There's actually been some results and some drugs that have been made going through like trials, some phase 3 trials. This one called Exoplanet was discontinued. I believe it was due to some side effects that came out. But yeah, there have been some results from that. But yeah, there are a large amount of adverse effects with this. Then finally, for small molecule treatments, we have nuclear import and export targeting. So basically what this means is that there are always molecules that are going inside and out, into and out of the nucleus in the cell. And that could be for DNA translation, things like that, or just like regulation in general, anything. And those things are really important for the cell to function and everything to work properly. So there's been some research into trying to like regulate the, to target the actual molecules that go in and out and help with like gene transcription, things like that. And there's been some results with that as well. There's been not as much attention to this field, especially with nuclear import molecules, meaning like molecules that go into the nucleus more. And there's been some results as well, though. So that was small molecule treatments. Now I'll be moving on to nucleic acid therapies, which is basically like using DNA, RNA molecules for targeting. So I'll be starting with ASOs, which are antisense oligonucleotides, and they're basically just short strands of genetic material, just short strands of like DNA, RNA, and they have a lot of like normal functions in the cell with gene translation and like protein expression and things like that. But basically they can be used to target whatever molecules you want, and they can construct them in such a way that you can target whatever molecule. And there's been some therapies that have been made targeting like genes, different proteins. You can see here, there's been QR110 that targets this CP290 and AZD9150, which targets the STAT3 gene. And there's been results in decreasing cancer with these. So there's a lot of potential since you can manipulate it to target whatever molecule you want. Then we have miRNAs, microRNAs, and small interfering RNAs. These are very similar to each other. And basically they're just small strands of RNA. And they can basically go and target any type of like mRNA gene, and they can go like thereby regulate that gene by targeting it. And there's been some research into it, but however, there's been some problems with it because they had some hindrances in the development. Yeah, exactly, but yeah. So there's a lot of options with this as well. So both of these options, the ASOs and these microRNAs, small interfering RNAs, they can be coded to basically target any molecule you want. So they'd be useful. So now I'll be moving on to the final section, which is antibody-based therapies. And basically, they've been using MABs, which are antibodies, to target different drugs. And basically, this field is like really new, so there hasn't been very much research yet. But there's been research into targeting this rank L, which is a receptor molecule, like I said before, and there's been like pretty good results with bone cancer and malignant hypercalcemia. It's been really helpful in like decreasing the cancer, but there's always like side effects. So, and then we also have these ADCs, which are antibody drug conjugates, and these will basically act like your typical antibody. They'll go and find a specific like molecule expressed on like a cancer cell surface, and then they'll go attack them. They'll deliver like a cytotoxic package that attacks them basically. So again, this is also a really new field. So there hasn't been much research done into it, but there's a lot of options that we can do with this. It's just that since it's such a new field, there's still a lot of kinks that we have to work out, and there's a lot of side effects at the moment. So those are basically the 4 different types of treatments that I looked into, and I picked just a couple different potential ways that we could go down. And what I found, I didn't have time to discuss the specifics of each one, and I can't rank each one here for you, but there are always going to be side effects if you're going to regulate a pathway, because a lot of those things are essential functions in the body, and if you try to suppress those pathways, sometimes you'll also be damaging those essential functions, and then you end up with a lot of these adverse side effects. So even then, however, I feel like it's really important that we do keep exploring, and as our technology keeps forward, that we keep exploring these alternative therapies so we can hopefully find a better way to fight cancer. And that should be it, basically. That's it for my paper. I have my paper linked here and references, but yeah, thank you for listening. If you have any questions, let me know.
That was great, Krey, and wow, what a overview of the space. I'm like super impressed. I'm a cancer immunologist myself, so really appreciate the work that you're doing and kind of listing out some of those different, potential treatment options. I would love to open it up. I think we have time for maybe one or two questions here before we move on to Nikhil, if there's any questions from the audience. But I can take it off. I know I was just curious, what you might have alluded to this, but kind of in your mind, what would be kind of your immediate, next steps after, doing all this research, and with your findings, what do you see for the field to really, what would be kind of the big thing for them to be focusing on next?
Yeah, so I really think that these newer fields like the antibody therapies and even the nucleic acid therapies they're not that new, but they're fairly new. I think there's a lot of potential with them. I think we should basically try to figure out different molecules and pathways that we can target, and then just basically go for it and explore all these different options. We have so many options. It's just that our research, like our experience with these therapies, aren't like quite there yet. But the only way we're going to go forward is if we test all these different options. So I think the best way is to move forward with these newer therapies, I believe.
That's great. If there aren't any more questions, I think just for sake of time here, we can move on to Nikhil. But thank you. It was really great. Thank you. Yeah.
Thank you.
Yeah, so can everyone see my screen?
Yep, it looks great.
All right, cool. So my paper was on how a reduction in registered nurse staffing impacts hospital centers, and this was a scoping literature review. So the COVID-19 pandemic has strained resources of our healthcare system in recent years, as increasing hospitalizations has skyrocketed the demand for care. Alongside tangible resources like masks and vaccines, the persistent shortages in the nurse labor market is creating drops in hospital profits, along with higher fatalities. Registered nurses, who make up 30% of our healthcare workforce, face the brunt of the pandemic, leading to an increasing rates of turnover from burnouts. For decades, nurses have been treated more as an operating cost rather than actual employees who deserve more than just a wage. And high-value care is defined as providing the best care possible, efficiently using resources, and achieving optimal results for each patient. And I believe that understanding how nurses impact the safety and the financial performance of hospitals will aid healthcare systems everywhere in improving the quality and efficiency of high-value care. So the database I used to conduct this literature review is called PubMed. I performed an advanced keyword search on PubMed using MESH, or medical subject heading terms, and I used the following combination: nurse staffing and hospitals, and then within parentheses, patient care or financial performance. So this search returned 563 articles ranging from January of 1975 to May 2022. 512 articles were deemed outside the scope of the review, and a systematic full-text review was performed on the remaining 51 articles. Finally, 20 met the inclusion and exclusion criteria. And further to strengthen the validity of my evidence, I used the Joanna Briggs Institute tool for systematic reviews and meta-analyses. This tool presented a set of criteria to objectively evaluate each article and score it on a scale from 1 to 11. And well over half of the articles scored at least an 8 out of 11. And I'll just leave 10 seconds here to look over my inclusion and exclusion criteria. So moving on to the results, I divided this into quality of patient care and financial performance. And even within quality of patient care, I split it based on patient mortality and patient complications. So 7 out of 20 articles unanimously agreed that a reduction in registered nurse staffing correlated with a higher mortality. Taranju et al. In 2006, in particular, identified that medical centers who employed more registered nurses per shift saw lower patient mortality over a span of 30 days. 13 out of the 20 articles then investigated how the rate of patient complications changed with lower registered nurse staffing. Complications were defined as missed patient care and hospital-acquired infections such as pneumonia, UTIs, and more. Overall, there was a unison conclusion that an inverse relationship existed, with lower nurse staffing units more prone to patient complications, along with an overall compromise in the quality of care. Wynandale et al. Reported that nurses are more susceptible to needle stick injuries as a result of understaffed hospital units, thus affecting their own ability to care for patients. And finally, results from a study conducted by Penoyer et al. Estimated a potential 26.7% decrease in infection rates if ICUs increased nurse staffing. And moving on to financial performance, when I investigated this relationship between a reduction in nurse staffing along with hospital financial performance, I found that a lack of uniformity existed within the relevant articles. 2 articles found that a reduction in staffing raised expenses as an additional cost from patient complications and nurse burnout were greater than the savings that resulted from cutting out labor. 3 studies concluded that an increase in nursing numbers lowered hospital costs. And finally, 2 articles saw a direct positive relationship between nurse staffing and hospital costs. Aside from our results, it's also important to gather current perspectives on the economic conflict between nurses and hospitals. So I decided to look what current nursing journals are saying about this conflict. The American Association for Critical Care Nurses argues that because hospitals simply view nurses as a percentage of their operating costs, these corporations slash costs by minimizing staffing and ignoring any adverse effect this change may have on both patients and nurses. Dr. Linda Eichen reports in the Journal of the American Medical Association that the addition of a patient onto a nurse's workload can equate to a 7% increase in the probability of 30-day mortality and failure to rescue, along with a 23% increase in the odds of nurse fatigue and job dissatisfaction. A survey conducted by the American College of Healthcare Executives, AIC for short, reported that hospital CEOs considered RN shortages or registered nurse shortages as a top concern to their organizations. A statement issued by the CEO of this nursing journal, Deborah Bowen, stated that hospital executives viewed staffing challenges as the top struggle in their hospitals and in their business, surpassing any other financial problems that they currently have. So how does this literature review fit into this overarching debate? Well, the study contributes to a discussion on the quality of nurse employment by organizing findings from various journals into one coherent study where connections between nurse staffing, patient care, and hospital costs are found. Assessing the economic implications of a weaker clinical environment adds layer complexity to the study within the healthcare system. And this review paper seeks to introduce readers to the basic interdisciplinary components of healthcare economics. A major step towards achieving high-value care or providing the best care through the efficient use of resources may be to view nurses as more than an operating cost. I believe that hospital administrators should consider dedicating a portion of their firm's resources to improve nurse staffing numbers and the well-being as a means of improving the safety and care of patients, because it may lead to an overall savings in the cost for medical centers, as noted in our evidence. Additionally, this literature review also has some limitations to it. Currently, an overall lack of transparency exists in hospital financials because of their private nature, leading to a publication bias. Information that benefits the public image of these private organizations may be more available. Finally, this review prioritized qualitative findings over quantitative. Thus, statistical analysis was not incorporated on the gathered data. And that's all I have so far. Thank you for listening. And if you have any questions, feel free to ask.
Thank you so much, Nikhil. This is a very timely topic, and I really appreciate it. We just had a hospital-wide kind of update, and just the clinical staffing shortages that we're dealing with, and even clinical staff burnout, and just having those discussions and trying to figure out ways to rectify it, remedy it, because it's happening. And so very, very important stuff. This was really great. We do have a question here from one of the audience members who asked, how can we dismantle the stereotype that nurses should mostly be female? You know, how can we encourage more people to go into nursing? What are your thoughts on that?
Yeah, so I think the nursing industry, or like the market so far, is becoming more diverse. There's definitely new positions opening, like nurse practitioning is definitely becoming much more important, and they're being given way more responsibilities than they have in the past. So I think currently, just like the value of nurses are changing. Even this pandemic has like shown more of a spotlight on just how valuable nurses are to hospitals around the world, shown by like how when nurses strike, hospitals are basically like limited, like extremely limited in their ability to function and provide high value care. And these gender stereotypes, they're definitely like improved a lot over these past years. Yeah, my study didn't really focus on that as an aspect, but yeah, I don't think people really view nurses as just female anymore. And it's definitely becoming a more inclusive community where everyone just has different values that's not really gender based, but really more like economically based and clinically based.
Yeah. I'm curious, what kind of drew you to this particular topic?
Yeah, so originally I was thinking of doing a more medical based research paper, but I was also taking AP economics and some other econ courses over the past year, and those really broadened my perspective on just how versatile economics is. And I figured that I could combine like these two aspects, or these like two interests that I have, and like add an interdisciplinary component to it. So that's why I decided to explore more of like healthcare economics and just like figure out the business structure of hospitals, and also how how economics and like clinical care goes like hand in hand, and how this affects a patient's well-being.
Very cool. What would be kind of your next steps, you know, now completing this work? How would you want to kind of take it further or build on it? What would you do next, do you think?
Yeah, I definitely think I want to start gathering my own data, or just like I definitely want to learn more about how to apply like statistical analysis into like findings. So rather than literature review, I want to go one step further and definitely like, gather data sets of my own, possibly like after like during college, when I can have like more access to more like data and like primary resources. I think that would be my next step. And also just going more into the economic structure of hospitals, because healthcare is like it is the largest component of our GDP. So it's definitely gonna become a larger issue in the future as we work to like make it more efficient.
Do you think you would, I'm just curious for, you know, how you're thinking about the next few years in school, and maybe what you might want to study in college, and are you thinking more of the econ side, or you mentioned medical? Or maybe are you trying to perhaps blend the two, continue with that interdisciplinary approach?
Yeah, I definitely think I want to go into the more econ or like statistics side of it. And I definitely still want to take like biology classes and like health policy classes during college. And that way I can definitely like I can still like capitalize on like my knowledge, or like just like get as like a wide experience, or like broad experience as possible. While also like specific, like focusing on one topic, I guess.
Yeah. Great. Well, great. So thank you so much, Nikhil, and thank you, Ari and Krey as well. I know we have a few more minutes left here. If there are any lingering questions from audience members, you know, please feel free to drop those in. You know, I'll stay on for a little bit here if any of those trickle in. But great job to all of you guys. Really fantastic work, and it's so mind-blowing to me what you guys were able to accomplish with these polygens projects. So you should feel really proud of yourselves. Yeah. And if there's no more questions from the audience, then you know, you guys are feel free to kind of head out and maybe go check out some of the other sessions that are happening currently right now. But it was really great having you guys here, and thank you for sharing your hard work with us. We do actually have, I think, so someone in our audience here just sent a question for, and I'd opened up to all of you guys if anyone wants to jump in. If you could do a second Polygens project, what would it be?
I definitely would want to stay in like the medical, like overall overarching medical field, but I am not exactly sure. I want to like stay in. I have an interest in like cancer biology, that kind of thing. So I might like want to approach it from a different perspective. I wouldn't immediately know like what that perspective would be, but I would want to stay in that kind of field.
Very cool.
Yeah.
I
If you ever
think
wanna-
oh, sorry, go
I
ahead.
was just going to say, Krey, if you ever want to talk about cancer bio, I'm a cancer biologist, so
Yeah.
and I
Sure.
so would love to chat with you more about that. Sorry, Nikhil,
Sure.
what were you going to say?
Yeah, I think I definitely want to use like either data science or even like data science and game theory to approach like a new discipline or a new industry and just like focus on like strategic interactions.
Cool. What about you, Ari? Any thoughts? What would be your second Polygens project if you were to do one?
Yeah, I think definitely because this one I kind of focused on like the groundwork. I think if I were to do another one, I would really want to look at actual data instead of just like generating stuff myself.
Yeah. And now that foundation is, laid, and so you can kind of just continue to build off of that, which is great. Wonderful. Any last questions from the audience? Or if you guys have questions for one another too, please feel free. Don't be shy. If not, then I think, let's see, we do have one. Oh, no. Okay. Well, I think with that, we can, close out our session here. Again, thank you guys so much. And yeah, enjoy the rest of your days.
Thank you
Thank
so
you.
much.
Yep. Bye.
Great day.